This lesson deals with peak detectors. You can find these notes in the ECE302 ebook in Chapter 2 starting on page 61. Let's first take a look at what's called a positive peak detector. It consists of a voltage source, a diode, and a capacitor, and also some series resistance associated with V sub S. We could replace this real diode with an ideal diode in a battery, whose value is VD on. The value of V sub S I'm going to pick to be a square wave, so it just has two values. That makes it a little bit easier to analyze. But what this is going to do is the same for any repetitive waveform. Now I solved this symbolically, but let me put some numbers here. Might make it a little bit easier to understand. Suppose that that's 5 volts, and this is minus 6. At t equals 0 plus, we have 5 volts. And initially, we have 0 volts across the capacitor. The voltage across the resistor and diode is equal to 5 volts minus 0, or 5 volts. Current's going to flow in this direction because I've got a large enough voltage greater than, say, 0.7. The current that's going to flow is the voltage across the resistor divided by the resistance. But if I have 5 volts here and roughly 0.7 here, I'd have 4.3 across here. I have 4.3 volts, or V sub A minus VD on, divided by R sub S. If R sub S were really small, this would be a spike of current. If we hit a capacitor with a spike of current, it can change very rapidly from one value to another. Not instantaneously, but quickly. In fact, we can calculate how fast because we'd have an RC time constant. If this was 1 microfarad and this was 1 ohm, we'd have a 1 microsecond time constant, and it would take 5 of those to get to steady state. Let's figure out where we're going to go. Wait long enough, where it's 5 time constants. What's the voltage across this capacitor? Well, in steady state, it's an open circuit, but it's never really an open circuit, just a big resistance. What that means is they have a little bit of current flowing. When the drop across here would be VD on, or say maybe 0.7, and go around the loop now and figure out V out. Where's it going to go from 0 to what value? V out, rise in voltage, equals the drops around the loop, minus 0.7, and then minus the drop across the resistor, plus 5. But if this current is really, really small, then the drop across here is going to be a small resistance times a small current, basically 0. In other words, if we had 1 ohm and 1 microamp, we'd have 1 microvolt. This is tending to minus 0.7 plus 5, or 4.3. It's going to do that in 5 time constants. If our time constant is 1 microsecond, and this is milliseconds, it would appear this jumps from 0 to 4.3 volts. What happens next? Well, when the input now goes to minus 6, we have 4.3 volts here, and this can't change instantaneously. But now if this goes to minus 6, then what's the voltage across the diode resistor again? Well, it's this node voltage, which is minus 6 minus 4.3. So this is a minus 10.3. The diode is off and no current flows. The output just stays where it is. Suppose that we go back to 5 volts again. Back over here now. What's the voltage across the diode resistor? Well, the capacitor voltage can't change instantaneously, so it's still 4.3. 5 volts minus 4.3 is 0.7. But if current is flowing, there's some drop across here. If this is 0.7 and current is flowing, then the voltage across here is 0. That means there's no current flowing. We're really sitting at the transition point of the diode. And basically we repeat what we just did. What this circuit does is that it takes the most positive peak and it grabs it, minus 1 diode drop. I prefer you memorize that instead of this formula here. But if you can remember what a circuit does in terms of a word description, we can use it to design. In fact, I'm going to use this to design what are called multiplier circuits. We just described this in here in words. If there's a positive peak detector, there should probably be a negative peak detector, and sure enough there is by just flipping the diode around. In our last analysis with a positive peak detector, we had a positive voltage across the load, and I showed this plus terminal for the capacitor because typically we use electrolytic capacitors and they are polarized. We need to keep the voltage across them positive with respect to the plus sign. Here the output's going to go negative, so I'm going to flip this over. Although when you do calculations it doesn't make any difference, but when you implement this it becomes very important. If you have a negative voltage across an electrolytic capacitor, it can explode. Please don't try that. Again, let's have a resistance associated with our source. And again, let me use some numbers here, make it a little bit easier to understand. So here's, say, 5 volts and minus 6 volts. Let's figure out what happens in our circuit. Initially at t equals 0 plus, we have 5 volts here. We have 0 volts across here. The voltage from here to here is equal to 5 volts minus 0, or 5 volts. But that means current wants to flow in this direction, and it can't. No current flows, and the voltage at the output stays at 0. Nothing happens now until we change our input from +5 to -6, so let's do that. Show it as a +6 this way. This voltage is -6 to ground, and this is 0, so it's going to have -6 volts across here. You can also write that as +6 volts that way. Current's going to flow through the capacitor, through the circuit, back around this way. There's 6 volts across here. How much voltage is across here? Well, it'd be 6 volts minus 0.7, so 5.3. So this would be equal to 5.3 volts. And the current would be that voltage divided by R sub S. If R sub S is small, this can become a really large spike in current, and that can cause this capacitor to go from one value to another. But again, it's in 5 time constants, so it depends on the scale that we're looking at for the time axis. So now we're going to wait until steady state, which will occur pretty quickly, and try to figure out where this voltage is going to go to. So I got 6 volts. This again looks like a big resistance. A little bit of current is flowing. The voltage across here would be roughly 0.7. And the voltage across here would be approximately 0. The rise in voltage equals a drop around the loops, 0.7 plus 0 minus 6. We're tending to minus 5.3. Or symbolically, minus B plus VD on, minus 6 plus 0.7. All right, what happens next? Well, nothing will happen until the input changes sign. Now we'll have 5 volts here. The output is still 5.3 in this direction. What's the voltage across the diode resistor? It's going to be this node voltage, which is minus 5.3 minus 5. We get 10.3 across here again, but negative. Diode is off, no current flows. Now let's see what happens next. So I get minus 6 volts. I'll put it as plus 6 volts in this direction. The output is still minus 5.3. Let's now find again the voltage across the diode resistor. So this node voltage minus this one. So minus 5.3 minus a minus 6. So we get 0.7 across here. If current's flowing, there's a drop across this resistor, but that would be equal to 0, because I need 0.7 across here. So no current flows. We're getting at a transition point, and the output just stays where it is. Symbolically, this is what the circuit does. It goes to minus B plus 1 diode drop. In other words, it's grabbing the most negative peak plus 1 diode drop. This is in steady state. There was a transient analysis in this case. In the previous one, there wasn't. I encourage you not to memorize this formula, but simply remember what this does. So this circuit does something, and very simply, it grabs the most negative peak in the circuit plus 1 diode drop and hangs on to it. This is all in words below here. Again, I did it symbolically. And these are peak detector circuits.